One of the things that happened, and it happened at Chernobyl, the Chernobyl accident in Russia, where they released a lot of radioactivity. Some of the radioactivity that's released is radioactive iodine. Right? So the people who were nearby, who ingested it, right, that iodine tends to want to go to your thyroid. Your body can handle a certain amount of radiation, right? As I said, we're getting it from the sun. You purposely go to the dentist and let them irradiate your head because learning that you have a cavity is very important compared to the small risk that you get in x-raying your head. But if you get too much iodine, especially radioactive, it'll concentrate and it will attack and potentially damage and kill your thyroid. Right? So one of the things people do to be prepared for that is you could have just iodine tablets.
A few years ago, I interviewed someone who they had previously been on a nuclear submarine in their service time here in the United States. And I was surprised to find out that these nuclear-powered subs could run for so long without having to refuel. Right. And then a couple, months later, I started researching different types of energy because I was buying this farm and looking at like ethanol fuel and different, just getting a little nerdy with it, in my spare time. And I was thinking to myself, okay, well, with the little I know about nuclear energy density, it seems like we should be using that. Like, it seems like a really smart thing. And then I was curious, I was like, why aren't we using it? I did some research. The best that I could come up with was that there were some issues with some nuclear power plants early on, and that sort of scared the public. And maybe that's why the technology didn't progress as far as or fast as it could have. So those are my very limited understanding and views. And so I want you to sort of like tell me, is that a correct assumption? Am I wrong? And sort of help me understand this concept a little bit better.
Yeah, sure. I think what you've learned is correct, but maybe part of the story, right? So the way I like to think about it is if you look at any product, right? Somebody introduces a product, it usually, if people like it, it starts to take off, right? But it usually plateaus at some level, right? And that where it plateaus is usually a combination of what it does, right? Like how many people do need this thing? What's its cost? What is the social acceptance? Are there reasons that are non-economic that people may or may not want it? And then what's the policy environment around that? Because we can influence decisions through policy, right? Tax breaks or other things that may not strictly make sense from a pure economic or social acceptance status, right? So we've introduced one generation of commercial nuclear power, right? So think of it as like the Model T of these energy systems. And when we started introducing them back in the 1960s, 70s, 80s, the U.S. regulatory system, it was all regulated utilities, right? So you told the utility, build this thing and we'll give you a fixed rate of return. Right? So you knew you were going to make money. You weren't going to get super rich off of it, but it was fixed. And under those conditions, the designers wanted to keep building bigger plants. Right? You got incentivized to build very large plants. So right now, about 20% of the U.S. electricity, 1 out of every 5 electrons, comes from nuclear in the U.S. But that is from only slightly less than 100 plants. Right. And part of it is nuclear has a huge energy density, meaning I get about 1 million times as much power out of a nuclear reaction as a single coal reaction. Right? That combined with the fact that we tried to build these very large plants meant we've got roughly 100 or so, and we get a lot out of them. But their size actually caused some issues. So when you talked about early accidents that influenced the public, one of these was at 3 Mile Island. It's sort of the one in the U.S. that people talk about. The most recent was at the Fukushima plant in Japan. And I think part of the response to those accidents from people is to get nervous about the technology. I think the other way people got nervous about the technology was in the early days. Most people in the 1940s, 50s, 60s, the first time they heard of nuclear was World War II weapons testing. Right? And so you just have this nuclear as a dangerous thing in your mind. And, nuclear engineers will get into these big arguments about, well, a bomb and a power plant don't operate the same, right? You can't make a power plant, blah, blah. I don't think that matters to the general public, right? I think they've seen in a couple cases that if you sort of lose control of the technology for whatever reason, then you can have these major accidents. It doesn't happen very often. Right. The safety record of these plants is great in general, but when something does happen, it is big and it's, I think, psychologically impactful. And so I think a couple things limited us to that 20%. Part of it was the social response, right? Some people just didn't want more plants. But also from an economic standpoint, starting in the 1990s around the country, we started changing the way we reimburse for electricity. It's different all over the country, but in some places it's deregulated markets and they compete based on cost. And so with that new reimbursement system, with natural gas getting extremely cheap due to fracking, with renewables getting cheap and also subsidized in a lot of cases, in certain cases, the nuke plants just couldn't compete, right? So I think you've got this combination of the gigantic nuclear plants that we have are only good in certain economic situations. The demand growth in the US isn't so much that we need a whole bunch more of these giant plants. And in a lot of places where you are building new electricity, it now just makes more sense to get something online really quickly. So you can get right now, so we've gotten very bad at building nuclear plants in the US, but the best case, the Koreans building the new plants in the United Arab Emirates, 5 years, right? Billions of dollars. Well, in a lot of cases, utilities don't want to do that, right? They just go get a natural gas plant. It's cheap. You can get it online faster. And so I think that's why I say it's part of what I think limits the new plants is sort of the societal acceptance. Part of it, though, is just the economics, right? And that this single product that we've got commercially doesn't always make sense. And if you look about overseas deployments, like a place like an African country whose demand growth is growing, one of these giant plants may be too much, right? If you imagine you put a gigantic plant online, right, and it's more than 20% of your total electricity in the country, you lose it, that's a big problem, right? You don't never want any single source to be such a big fraction. So I think what's exciting about nuclear now, we're at this phase where either all those old plants we built will get shut down and that'll be the end of it, or you got lots of companies out there. Bill Gates' company is probably the most famous because Bill Gates is the most famous, right, who've got these different ideas for different sizes, different uses that might make sense in sort of modern energy markets. And we'll see. Right, so I think that's kind of a long answer to what you asked.
Yeah.
But
no, it's good though. So for example, like the submarine we were talking about earlier, that's a smaller nuclear, would you call a nuclear powered engine? Is that how you would refer to it?
Yeah, essentially, right? That reactor on the submarine produces all the power you need to move the ship through the water, right? As well as all the electricity that you need for heat, power, lights, equipment. Yep.
So why, and I'm just throwing stuff out here.
Yeah, sure.
That seems like a more decentralized way. Like, why don't I just have a nuclear reactor for my house instead of having a multi-billion-dollar nuclear reactor in the city to supply all of this stuff? Are people going in that direction, or is that not economically feasible currently?
Yeah. So with all these new plants I'm talking about, people are just getting to the point of building the first demonstration. So whether it's economically feasible, I think it's a question to be answered. Right. I mean, they're competing with fairly cheap renewables and natural gas. But in some cases, you're absolutely right. They're looking at much, much smaller plants. So the term the nuclear engineers use is micro reactors. But think of it as about 1/1000th to 1/100th the size of a typical plant. Or if you've been fortunate enough to ever visit a university that's got a research reactor, that's about the size. Right. And so where would you use something like that? Well, some of the places people think about are look at remote northern communities, Canada, Alaska. In a lot of cases, the weather is such that you can only bring fuel in at certain times a year. Right. I mean, and you have to have enough for the winter. And it's typically diesel and it's expensive, much more expensive energy than here in the continental US. So it's dirty, it's expensive. Well, could you replace that with what looks like a very small nuclear reactor. I mean, smaller communities, you don't need a ton, right? So that's one thing people are looking at. But then if you do build those and people start building them, then you start seeing other potential opportunities, right? So defense bases like to have secure power, right? They get power from the grid, but if that goes down, they want their own very secure backup. Well, maybe if you had a very small reactor, you could use it in that situation, right? Lots of people are talking about not wanting to rely on the grid, but having more of a microgrid, local distributed power. Typically, they talk about that in terms of wind, solar, right? So you build your own solar resources or wind, but you always have to have some backup, right? Might be batteries. We don't have batteries yet that are good enough to do season to season storage. So maybe a small reactor would make sense in that case. And in the US, we've always used the reactors for electricity. There are other countries that use them for electricity and like district heating. So I take the heat from the reactor and just run it through pipes in people's houses to heat it up. So a lot of people are thinking about applications like that. And the reason they think about maybe Alaska, Northern Canada first is, whenever you build something, you get better at it over time, right? And that drives the cost curve down. That's what's happening with renewables. So the thought is, well, maybe if you can start building them in northern communities, but you build enough, then you start to drive the costs down. Those northern communities right now are paying a lot more for power anyway, so you don't have to be as cheap, right, to get into the market there. I think that's some of the thinking.
What's the cost? The submarine nuclear reactor. Let's say that cost X, right? What is the comparison to how much the actual nuclear material cost? Is most of the cost in the machine, or is most of the cost in the material?
Yep. So that's a good question. So first, I should differentiate. Probably don't look at submarine reactor costs, right? If you can get that as a good comparison to civilian, because they're very specialized machines and they need to do a lot more, right? So as an example, civilian machine, you really just want to get it up, steady state, make power. But you're on the submarine, right? You've got to do things like go from 0 to as fast as you can because somebody's shooting torpedoes at you, right? It's a high performance. It's like it's like the high performance Ferrari version of a reactor. So it costs more because
I need that for my house though, just so you know.
Yeah, well,
there. I've got kids. Yeah.
Yeah. When the speakers come on and you need them loud, you don't want to have to wait. Yeah, I get it. Anyway, so the costs associated with once you've got the reactor running, right? The fuel is actually fairly cheap. Right, so a lot of the costs traditionally, and thinking with the big traditional reactors, a lot of money to build them, a lot of money just in interest, right? As you take out the bank loans and you're building this thing, you don't make any money until you start selling electricity. If it takes you a decade to finish it, 5 to 10 years, you're just carrying those interest costs for a while. So there are interest costs. And with traditional reactors, and this is another reason why people are thinking the smaller ones may differentiate, is there's a lot of operators. Right, and a lot of security personnel associated with the big reactors. So to be proven, if people can get these regulated and approved with smaller staff. But I think that those are the things they're looking at. Build them in a manufacturing way so that for a fixed amount of material, you just get better at putting them together. Traditional reactors, you built them all on site. It was a big, huge construction project. People are hoping build them in a factory the way you would a car, right? Drive the costs down. But once you get them going, the fuel is actually pretty inexpensive compared to
how do you get that fuel? How do you get that material? Well, first of all, it's called fuel, not material. I was just saying, I know what to say.
We call it fuel.
So, all right. So how do you actually mine that? Where does the nuclear fuel come from?
Yep. So there's a few countries in the world that have big, just like any other thing that you mine, right? There are places in the world that have lots of uranium. Australia, Kazakhstan, Canada, Russia. The U.S. has a lot of uranium reserves in Wyoming. In the past, near term, though, we've stopped doing a lot of our own mining and we've been importing. Okay? And this is why, if you're reading in the news, the concerns with Russian fuel is that they provide a lot of the fuel into the international markets. Right? Yeah. And so people are suddenly saying, look, you can't trust the Russians for your energy security, or we don't want to buy their fuel because they're doing awful things, and we don't want to support that. So we're in this big pivot right now. But there are other places in the world that you can mine uranium from. Right.
And if I come across uranium in the wild, what does that look like?
It just looks like a rock.
Just look like a rock?
Yeah. I mean, I don't think you would, a geologist might know. You wouldn't know unless maybe you had like a radiation detector you could hold up to it. It's uranium in the wild is not really that radioactive, but you could measure it. Right?
Okay. So you sort of crush these rocks and sort of somehow extract it from.
Yeah, it's a bit of a complicated process. So you have to extract it. It turns out that within uranium, so the way you get power in a nuclear reactor is something called a fission, right? And you split an atom and it just gives off a tremendous amount of energy. Not every uranium atom fissions very easily, right? The kind that do is it's slightly less than 1% of natural uranium. So it's a little bit of a complicated process. You go in, you dig up, okay, I've got a bunch of uranium. And you say, well, I want this specific part. So I need to find a way to concentrate that part, right? And this involves some chemical processing, some separations by mass. It's kind of a big industrial process to go from natural uranium into something that is the compositions that you want for the fuel. Then once you've got that, then it's just ceramic processing, right? You take things and you press them into little cylinders. And so after you go through all those processes, you've got little cylinders and you stack them up in a tube, right? And you got a number of those tubes that you put together in assembly, and a bunch of those assembly you put into a plant. But basically it's rock, process the rock to get the right concentrations, press that into the fuel, and then you're good to go.
Do you think that nuclear would be useful for like rocket ships for space, or once you're in space to have nuclear plants floating around there, or is it not good for space?
Yeah, actually, it's probably necessary in a way that's counterintuitive to most people, right? So it turns out that the world is naturally radioactive, right? The sun is giving off a lot of radiation, and some of it gets to us as humans. But the reason we don't get too much is the Earth's atmosphere blocks it, right? Well, if you're a rocket ship commander, right, as soon as you leave the Earth's atmosphere, then you're potentially subject to really high radiation fields, especially if there's like a solar flare or something. So let's imagine you want to go from here to Mars, right? And you don't, because it would just take more fuel, right? You don't want to have to carry a lot of heavy materials on your rocket that would shield you from the sun's radiation. So you want to get there as fast as possible, right? And so to get there as fast as possible, you need something that gives you a lot of power in a very short amount of time to give you like a really strong impulse. So, right now we go to the moon, which in space terms is not that far away, just using chemical rockets. But if you start to look at needing to get to Mars or further and wanting to do it in relative short periods of time, you need something that really gives you a powerful push. And so you look at nuclear because, as I said, it's 1 million times more power per reaction than a chemical reaction. And then if you try to do it with like deployable solar panels, the further and further you get from the sun, the less you're picking up. Right? So that doesn't work very well. So there's lots of thoughts. If you look at all the literature about people who want to do Mars missions or even remote power stations, if you were on Mars, it almost always defaults to nuclear. Right? And you get into questions then about, do you want to launch from Earth using a nuclear rocket, or do you want to launch something using chemical rockets and then start the nuclear processes once you're clear, right, of the Earth's orbit? Because if you had an accident, you don't want to have a nuclear rocket that's going to spread contaminated material. Right?
Yeah.
So it's a long answer, right? But I think most people that think about long-term space missions, you almost have to get back to nuclear. Nothing else gives you enough power for the mass of the fuel that you're carrying.
Yeah, and you reminded me, I was watching some interviews with some astronauts and they were saying that because they didn't have the magnetic or the atmosphere from the Earth, at night when they're sleeping, like they'll get these bright flashes of lights like on the back of their eyelids because those are some sort of like particles hitting their retinas that are normally blocked out by
right.
the atmosphere.
Yeah.
But one thing you mentioned, and I've heard it a lot, like people will use chemical rockets and then they'll say nuclear, but like what's the differentiation? I mean, isn't nuclear like a chemical reaction and like chemical rock? Like, can you help me understand the differences?
Yeah. I'm going to take you back to early chemistry and physics if you've taken that. So you remember the model of an atom, right? You got like neutrons and protons in a nucleus, and then you got electrons surrounding it. All right. So when somebody talks about a chemical reaction, it's electrons doing things with other electrons, right? So for instance, if I've got some pure sodium and I've got some pure chlorine and I get them close to each other, it turns out they want to share electrons, right? They're happier, and then you get salt, right? So when you say sodium chloride is salt, right? So that's a chemical reaction, right? But it's just those electrons. Nuclear, it's all happening in the nucleus, right? And the way the reactions happen are different, but much more powerful, right? So it's rare. So when people differentiate between a nuclear reaction and a chemical reaction, that's the difference. Are electrons doing things? Are you doing things with nucleus? And then the ramifications of that are the amount of power you can get per reaction.
Excellent. So I wanted, since we're going back, we just kind of like jumped into everything because I was so excited. Can you give me like your brief experience in this nuclear field? What you did growing up and what you've been doing professionally and where you're at today?
Yeah. So, I mean, growing up, that's not interesting. Like typical Midwest high school kid, went to high school, watched Godzilla movies on TV. Yeah, nothing. But I got into nuclear actually because I lucked out. I got a Navy ROTC scholarship to go to college. I mean, it's a random event, right? Recruiter shows up at school, and I don't know anything about the Navy, but I went and filled out the paperwork, and then suddenly they're offering me enough money to go to Northwestern University. So I'm like, sure, I'll do it. But that scholarship, then they'll pay for your college, but then you owe them. I owed them 5 years active duty. And so then you get a discussion, well, what do you do in the Navy? And they say, it's real easy. Either you're going to be an airplane pilot, you're going to be on a surface ship, you're going to be a Marine Corps officer, you're going to be on a submarine. And I don't know why, but my teenage brain said the submarine thing sounds fun, right, compared to the others. And then I learned that the submarine's powered by the nuclear reactor. And I had actually applied to be a computer scientist when I did my college applications, but I switched my major to nuclear. So like it's, how did I get into nuclear? Typical serendipitous random things that happen to high school age kids, right? But then I got that degree and I spent 7 years active duty in the Navy, right? So I went through Navy nuclear power training, spent 3.5 years on the submarine. They sent me to teach physics for a couple of years at the Naval Academy. I then decided to leave active duty. I stayed in the reserves for another 17 years. So I'm a retired Navy captain at this point. But then I left active duty and I went back here to Michigan where I am now, got my Ph.D. I'm studying nuclear engineering, specifically like how materials react in nuclear systems. And then over the course of the years after I got my degree, I worked as a staff research scientist at Argonne National Lab. It's a big Department of Energy research lab. I then got a faculty position at the University of Wisconsin. I was there for about 15 years, but in the middle, I took a leave of absence and I went out to Idaho as like a senior, and I'm older now, so I'm a senior executive, kind of number 2 person at the lab. It was called Deputy for Science and Technology. So imagine everything this lab does, the science and technology things. I sort of coordinated that for the lab director, the boss. Did that for a few years, and then I had the opportunity to go spend time in Washington, D.C. at a think tank, like learning about public policy approaches to nuclear. Then I went back to Wisconsin for a couple of years, and then I got offered this position at Michigan. So now I'm the chair of the nuclear engineering department here at Michigan, and I'm kind of doing a combination of researchy things and administrative things and public policy things that all make sense if you look at my history. So a little bit of operating nuclear plants on the reactor, a little bit of research, a little bit of teaching, a little bit of policy.
That is so cool. You've got a wide breadth of experience. That's awesome. I'm curious. Where do I want to go with this? I definitely want to talk about nuclear weapons. So my questions are, what is the smallest nuclear weapon that you're aware of?
So, I'm not a huge weapons expert. So, I think I've read that like the Soviets have these tactical, so like the size you could put on a missile, right? It's still, I think, I'm going to be somewhat ignorant here because I don't know. I don't know off the top of my head like the number of kilotons, right? But even a small nuclear weapon is a lot, right? But I think that's the size that I've read about, sort of things that you could shoot on a missile, right? Like a smaller missile.
What are you talking about with your peers right now? What are the hot topics amongst people of your expertise level in nuclear going on? What's going on?
Yeah, I think it's these advanced reactors we started to talk about before. So for a lot of my career, the energy in looking at new reactors was pretty much a research function, right? We've got these big, really impressive national laboratories that the Department of Energy runs, but they're research facilities. They're not really sort of commercial companies. Well, starting about 5-6 years ago, maybe a little earlier, a large number of privately funded efforts, small companies, just started showing up, right? And as I said, they're thinking about nuclear in a much different way, right? As I said, first generation nuclear was very, very large electricity production plants. And now they're looking at varying sizes for electricity, but also varying functions. Do I supply heat? So like an industry that uses lots of high temperature heat, chemical industries, steel industries, they may burn a lot of natural gas to do that. But if you're concerned with climate change and release of carbon dioxide into the atmosphere, you wouldn't want to burn gas unless you can sequester all of the CO2, that comes off of that. So maybe you could build a reactor that just direct heat to a big industry. Never skip the electricity. So I think a lot of the sort of excitement around nuclear in the past decade-ish, I'd say, is around those companies, those ideas. But then also in public policy space, can you do things, all right, to help them succeed? So as an example, one of the first things that the U.S. government did was started a program. It's called GAIN, Gateway for Accelerated Innovation in Nuclear. But the general idea is these big research laboratories have a lot of really specialized capability, right? GAIN tried to make it accessible to all of these companies, right? So they wouldn't have to rebuild the specialized equipment. So we did that. And now they've got a big private public cost share program to try to build first generation demos of some of these new ideas. So I think that's where all the interest is. And as I said, I think Bill Gates' company, it's called TerraPower. He's been on 60 Minutes. It's in the news. He's not the only one, but he's certainly out there in front of a lot of the companies. But one of many.
So there are programs out there, both in the private and the public sector, that are helping spur like innovation in this industry. That's cool.
Much more than we've seen for a long time.
Yeah, I tell them to hurry up. I want a nuclear watch, right? Nuclear powered iPhone. Never have to charge it, right?
Yeah, there you go.
Yeah. So I'm curious. Maybe you might know this. So I just bought a farm about an hour outside of Nashville, and I was thinking the other day, I was like, oh, what would happen if a nuclear bomb went off in Nashville? And how would that impact me being an hour away out in the sticks, And is there anything I could be doing, any sort of supplies I should have, and put in we've got like a bomb shelter, tornado shelter thing, tablets for purifying water, anything. Like, what would you do if your family lived 1 hour outside of a city that got a nuclear bomb dropped on it?
I think the things. So first of all, if they drop a nuclear bomb on a city, it's going to be horrible no matter what. Right. But I think the few things that you could do. One of the things. So our bodies, right, tend to use chemicals in certain ways. So I'll use your thyroid as an example. Your thyroid needs iodine just to function, right? One of the things that happened, and it happened at Chernobyl, the Chernobyl accident in Russia, where they released a lot of radioactivity. Some of the radioactivity that's released is radioactive iodine. Right? So the people who were nearby, who ingested it, right, that iodine tends to want to go to your thyroid. Your body can handle a certain amount of radiation, right? As I said, we're getting it from the sun. You purposely go to the dentist and let them irradiate your head because learning that you have a cavity is very important compared to the small risk that you get in x-raying your head. But if you get too much iodine, especially radioactive, it'll concentrate and it will attack and potentially damage and kill your thyroid, right? So one of the things people do to be prepared for that is you could have just iodine tablets, right? Because if you ingest the iodine before radioactive iodine gets to you, then your thyroid gets full. It only can use so much. Then it won't ingest new, right? So that's something, right?
Okay.
The other thing is when you try to protect yourself from excessive amounts of radiation, right? There's two things you worry about. One, some radiation cannot even penetrate your skin, but we don't want to inhale it because then it's inside, right? So little things like if you were in this situation and you had the ability to go underground or have a gas mask or something, it would. But honestly, I don't. You could do all this, right? But I actually think just the damage from a nuclear blast is so significant compared to this that I think the best thing you could do is like try to convince your congressman to get the world to decrease the number of nuclear weapons, to be honest with you.
Yes, right. No, it's an interesting question. I think about it. What do you have kids?
I do not have kids. No, I have bobbleheads.
You have bobbleheads. They're very similar. Yeah. But no, when I started to have kids, I started to like sort of care about this stuff more.
Yeah.
And it's being background with engineering, like software engineering, and thinking about things objectively. It's like, okay, well, if a bomb did hit, well, first of all, like all the fuel, all the supply chains, like everything's shut down anyways. If the crops are contaminated from like nuclear fallout, then you only have this much food anyways. And then what's the quality of like life going to be? And are you going to be able to get somewhere safe? There's all these questions, but when you're doing a podcast, you've got to ask a question, what could you be doing? And I'm so glad that you explained the iodine thing to me because I don't have any iodine but I've, researched and I've by research, I mean, I searched on Amazon for like fallout supplies type stuff and people are like iodine, but I never understood how it actually works. So I'm going to regurgitate it. You tell me if I've got it right. Your thyroid needs iodine.
Yep.
And you'll ingest sort of like the nuclear contaminated iodine and that'll kill you. But if you actually ingest like the pure iodine that you have stored safely, that'll fill your need up for it. And then it's not going to process that other iodine.
Yep, I'd only make one small clarification: is that the thyroid cancer doesn't usually kill you. Okay. It's something that they remove your thyroid. It limits your functionality, right? But in most cases, that one doesn't kill you. It's not good in any way, right? But it's the iodine radiation events in Chernobyl. Lots of surgeries and people having their thyroids removed. But it's something that is curable.
What's the thing that kills you the most other than the blast itself?
Yeah, well, it's definitely the blast. And then if you get a lot of just too much radiation, right, of any type, your body can't handle it, right? So we know from studies of the World War II bomb victims in Japan, they did estimates of how much radiation people got. And well, I said your body can recover from a certain amount. Too much, and it just can't repair itself fast enough. Right, and that's in working in nuclear systems. We've got all these radiation protection rules. So if you're a worker, right, you wear these little monitors, and we keep track of how much radiation you get. And if you reach the limit in a year, you're just not allowed to do that job anymore. Now, I say that, and the way we structure the work rules, people very rarely get to these limits, right? And there's like the regulators limits, then companies usually say, well, I'm only going to let you get to a 1/10 of that because we don't want you to even be close. But yeah, so we do know if you get too much radiation, you can just overwhelm your body's ability to repair the cells.
I want to talk a little bit about career development and progression in the nuclear field. So sure. We get a wide range of listeners from, founders of large technology companies to people who want to become from individual engineers to like management or leadership, all the way to the next generation who's just, in high school, college type stuff, looking for what they're going to be doing. Nuclear is a very exciting word. Like I never see that as a boring subject. What sort of advice would you give or thoughts do you have for people who are early on in their careers, maybe high school or college, and they think nuclear sounds exciting? They also like technology, and they're figuring out if that's an area that they want to go spend some time in.
Yeah, so I would say first, recognize that nuclear is probably broader than you imagine, right? So we've been talking a lot about power, right? But a lot of medicine uses nuclear or radiological processes, right? Not only to diagnose you, but to treat you, right? So as an example, let's say I'll use go back to the thyroid again, right? If I can measure radiation, I can detect it. We built detectors, we can do that, right? And let's say I want to understand how your body's functioning, right? I can actually have you ingest a small amount of radiation, and then I can watch those signals coming off of your body to see how your body is reacting, right? So your body, just like the iodine case, the body's reacting because it's a chemical that it wants. But if I give you a radioactive version of that chemical, I can follow it through your body, and then I can say, oh, I can image now and see what your problem is. And we do that all the time in nuclear medicine. Then, in some cases, then if we know, for instance, you have a cancer and we want to try to kill it, we can try to put very close to that cancer a radioactive source, enough that we design it so it's doing a lot of damage locally to the tumor, hopefully minimizing the damage to the rest of your body, right? But it's a way of killing like cancerous cells. So the one thing is, if you're interested in nuclear, you could say, well, I want to do something in power. But you could say, I want to do something in medicine, in imaging. And then the imaging thing is also seen in like national security, right? Let's say somebody's trying to smuggle radioactive material in through a port, right? And you don't want to like search every single container. But people have developed ways to shoot particles in a way that causes a nuclear reaction that we can measure. But it's only there if the thing they're trying to smuggle is in there, right? If it's not, then the container would seem empty, right? So there's all sorts of power, medicine, but also sort of national security type things that we do with nuclear. And then there's industrial uses. Like say you're drilling a deep well, and you want to know what it looks like down there, we can use little radiation signals and detection to see what's going on down there. So there's like a ton of things that you can do in nuclear that people don't even realize. So that all said, then you have to decide, well, do you want to get into nuclear technology, right? And there's lots of ways you could do that. Right? It tends to be a very chemistry, physics, math heavy field. But you can get into nuclear all the way from the things I've done, research, right, down to plant operations, people that just run the plant, know how it operates. That includes people that are specialists in maintenance of nuclear systems, right? Nuclear power plants have typically a lot of sort of high paid technical union jobs compared to other things. And I think even using the submarine as an example, right? You need people that understand the reactor, but you need people who understand how you use the power from the reactor to make electricity, right? So it's like all different fields of engineering get involved. And then you can be business, you can be communications. I think you almost do anything. But the first thing would be figure out what it is about nuclear that intrigues you, right? And it's probably bigger than you know.
That is cool. Yeah, you just expanded my mind because I'd heard about a number of those. My brother and stepmom are both physicians, so I remember they had told me something a couple years ago about it. But one question that I have is, we're talking about all these different uses of nuclear, and so we're using this one word to describe all these uses. Is it the same exact reaction that we're just doing at different levels of intensity, or are there different types of nuclear reactions?
Yep. Different types of nuclear reactions. So when we started out talking about power, right, and I mentioned it's 1,000,000 times more energy, that's a very specific reaction called a fission. Okay? A lot of the medical things, we're talking about different reactions, right? Or the national security. Like, so if I have an example where I want to measure, is there a certain set of chemicals here, right? I can do that through nuclear reactions, right? But those are very different than the fission that causes power. So some of the principles are the same, right? Like, how do I make a reaction happen? When I make the reaction happen, what comes off of it? Because I talk about radioactive material as if it's a single thing, but there's lots of different types. And so, you target your need with different reactions. So it's much more, it's not a single thing. It's a sort of range of different reactions that we use depending on, is it a medical application? Is it a power application? Is it an industrial application?
So it's a range of different reactions and a range of different materials. Like there could be different types of uranium or different. Is there any nuclear material that's not uranium?
Oh, yeah. Yep. So there's different kinds of uranium, right? Yeah. But then there are other materials like thorium, plutonium, and then sort of everything in the periodic. Even if you talk about nuclear fusion, which you may have heard of, right? Mm-hmm. In nuclear fission, we're breaking apart really heavy things. Nuclear fusion, we're trying to put together very light things, but they're still nuclear reactions. As I said, it's things that are going on at the level of the nucleus. And so, for anyone and your listeners who know what a periodic table of elements is, it lists every single material that there is, right? Iron, chromium, everything. Right? You can do nuclear things across the entire world. Right? It just depends on what you're trying to do.
Okay. All right. And so give me a couple of different examples. Like you mentioned fissions, how you do, you sort of, for lack of a better term, you incite them for the explosion, right? How would you excite the nuclear? What type of process would it be for something lighter, like the some medical version of it? Like, what are you actually doing to it?
Yep. So I'll give you 3 examples. So fission's the first one we talked about, and what I do is I take something like uranium, and I can do a nuclear reaction that makes it split into 2 pieces, and it just gives off a lot of energy. That's one. If I go all the way to the really light elements, it turns out I can take 2 really light things. So let's say like a hydrogen atom and a hydrogen atom, and I can fire them at each other. And if I get them going fast enough, I can get the nucleus to merge. And it turns out that also gives off a ton of energy for a different reason. Right? So that's the second example. Those are both power related. For a medical example, there's something called boron neutron capture therapy. Sounds really fancy. But if I have a boron atom, I can have a reaction where it will absorb a neutron, and then it will split into 2 pieces, right? And people use this for medical in the sense that if I can get the boron in your body where I want, right? Let's say next to a tumor, then I can then shoot a particle into you that hits the boron captures it, then it splits into 2 pieces. Those pieces have a lot of energy, and they'll like run into and damage whatever's nearby. Right? So if I put the boron near your tumor, right, what I'm doing is very locally through these reactions concentrating a bunch of energy. And if I do it right, that energy kills the local cancer cell without damaging a lot of the good tissue around it. So it's 3 very different things. In each case, it's nuclear, right, because I'm getting things to happen at the nucleus level, right, but for very different reasons. Right? I'm releasing energy, but I'm trying to do very different things with it.
This is so cool. I got to be honest. I feel like a kid in the candy shop learning about all of this stuff and how it's always so humbling to go into other fields and realize how deep they are. I mean, come on, The amount of research to figure out that you could do this boron concept where you're shooting things at it and it's splitting like that. That is just, it makes me happy. And it gives me optimism and faith in humanity.
Yeah. Well, I mean, you can do that's what's cool about technology, right? You can do a lot of clever things. And, at the same time, though, you have to realize the limits or the ethical implications of using it wrongly, right? So I can talk about all these cool things you can do with nuclear power or nuclear reactions. On the other end of it, people have figured out how to make a very destructive weapon out of it, right? And we don't like that, right? We figured out how to pass information technology in amazing ways. Like when I was a kid, right? We had like 3 television channels and it came into my TV through the airways. Like there was no internet, right? We can do all this stuff and it's super cool. And we can control things in a super cool way. But at the same time, people can cyber attack that and cause a lot of damage and shut down our systems and take over our bank accounts, right? So it's all, part of being a technologist is figuring out how to do cool things. And I think the other part of it is figuring out how will people respond to it, right? What are the problematic parts of the technology, and figuring out ways to get the most out of the good parts and minimize the bad parts from it, right? It's being a scientist can be pretty cool.
Yes, I've absolutely chosen the path of light. I've chosen, like, when you have the great battle of good versus evil, I realized real quick that, like, it's harder, but it's more rewarding to choose the good path. So, well, this has been great, man. I really appreciate. Do you have books out there? I want to make sure we plug anything. Do you have books or causes or anything we can direct people to?
Yeah, I would just say, so the thing we're trying to do at Michigan, I'm in a nuclear engineering department, and most nuclear engineering departments are very technology focused. I personally started something here. We call it fastest path to zero, meaning zero carbon, right? And it's really like, how do you answer some of these, not just technology questions, but the economic and the social and the policy things we talked about in order to make new generations of nuclear possible, right? And we're doing some economic studies. We're doing some sort of social, to your first question, some social engagement questions, right? How do you design technology in a way that people are most likely to want it, where the benefits are better than the risks, right? So we're trying to look at a lot of those non-technology things to try to optimize what we do with the technology. So we call it fastest path to zero. So if people want to check out what we're doing, it'd be fun.